Hey everyone, welcome to Gradegetter. My name is Taylor, and today we are continuing our series of videos where we work through a practice test for the SAT. This series is designed to go through a sample math test of the SAT to help you get a feel for what kind of questions will be on the test and how to study for them. Alright, let's make the SAT make sense. In part one of this series, we introduced the SAT math test, and we actually worked through the first couple of problems together. We are taking our time working through these questions so that you know the concepts of these problems and how to solve them. Today, we are picking up where we left off from our last video. Alright, a quick word about these problems we're about to solve. Remember that the SAT math test is divided up into two sections. One section where you're not allowed to use a calculator, and a second section where you are allowed to use a calculator. Now the problems in this video, you are allowed to use a calculator. So just keep that in mind as you're solving these problems. I may pull up a calculator as well. So that's a resource that you can use. But just remember, you're not allowed to use a calculator on all of the SAT math test. Just on the section where they say it's okay. Alright, so for this problem it says that Taylor is 6 feet tall. If 1 foot is equal to approximately 0.3 meters, then which of the following is closest to Taylor's height in meters? So this is going to be a conversion problem. I'm going to write down our original value for Taylor's height, which is 6 feet. So 6 feet, and then I've got to convert feet into meters, into a certain number of meters. So I'm going to do that using what's called a related rate. So the related rate is that 1 foot, for every 1 foot, it's approximately 0.3 meters. Okay, so do I multiply this by 1 foot over 0.3 meters? Or should I multiply 6 feet by 0.3 meters, 0.3 meters per 1 foot? How do I know which unit goes on top and which unit goes on bottom? I know I'm going to use this ratio, but I could either do 1 foot over 0.3 meters or 0.3 meters over 1 foot. And the way you know is to see which unit gets canceled out. So doing it this way, I get feet in the numerator over feet in the denominator. So these actually end up canceling out, which is what I want. And I'm just left with meters. And that's what we're trying to solve for, right? We're trying to find Taylor's height in meters. So the units that I want to cancel out are feet, and what I want to be left with is meters. If I did it the other way, I would get feet times feet over meters. That would be feet squared over meters, which doesn't make any sense. So you can really use units to your advantage here. So we have our ratio in the correct position where the feet cancels out with feet, and now we're just multiplying. Right, this is technically a fraction, 6 feet over 1. And we're multiplying it by this fraction of 0.3 over 1. Fractions just multiply straight across, so numerator multiplies times numerator over denominator times denominator. So 6 times 0.3, you could probably do this in your head. I think it's going to be 1.8, but remember we're allowed to use a calculator. So I'm going to go ahead and bring one up. So 6 times 0.3 is, it's 1.8. So 1.8 meters over 1. So that is our answer here, which is A. Alright, our next problem says that a developer is creating a plan for a 44-acre park that includes a 4-acre lake that cannot be developed. If 8 to 10 acres, inclusive, that's a keyword we'll come back to, must be reserved for soccer fields, which of the following inequalities shows all possible values for P? the amount of land that within the park that is available for development. All right, well, first of all, let's see how much of this land is available for development, not including the soccer fields. And so we have 44 total acres available, but 4 acres due to a lake cannot be developed. So we've got a total of 40 acres that we're able to use for development. However, we've got to save 8 to 10 acres for soccer fields. Now, let's say S represents the acreage for soccer fields. The acreage available to develop soccer fields is greater than or equal to 8 and less than or equal to 10. And this equal to comes from this word, the inclusive. So that means it can include 8 acres or 10 acres. So it's greater than or equal to and less than or equal to, right? Rather than just less than or greater than or less than. So that's all that word means. So I'm going to see what 40 minus 8 would be and 40 minus 10 would be. And that's going to be the total amount of land available for development. So 40 minus 8 is 32, and 40 minus 10 is 30. Well, P has to be in between these values, and it can't be greater than 32, so it's got to be less than or equal to 32, but more than or equal to 30. So our answer is going to be B, right? It's the same answer that I've written. It's just that our inequality signs are different. So if I was to rewrite this, I could write it like greater than or equal to 30, less than or equal to 32. So this is our answer for this question. We have more problems to solve, but before we move on, I just wanted to let you know that Gradegetter has a whole library of videos to help make you a better student. But if you want more personal interaction, Gradegetter also offers private one-on-one tutoring, where the first 30 minutes are free with no obligation to make sure that the tutor is a good fit for you. So if you're looking for some extra help, then head to our website at gradegetter.com. Now back to the video. All right, for this problem, we're given a bunch of information. We've got this graph, and we've got some information that they give us down here that explains some of the graph. It says that the scatter plot above shows the fuel efficiency in miles per gallon of a variety of vehicles weighing between 1.5 and 4 tons. Based on the line of best fit to the data presented, that's this dark line here, this solid line that I've highlighted in orange. That's the line of best fit. Which of the following, so here's our question, which of the following is the closest to the expected miles per gallon of a vehicle that weighs 3 tons? So we're going to go to look at the axis that has the weight of the vehicles, and we're going to look at this line that has a vehicle weighing 3 tons. And we'll go all the way up to this best line of fit, which is right here, and see where it intersects now our miles per gallon. So it looks like it's in between 20 and 25, but closer to 25. So it can't be A, C, or D. So our answer has got to be B. So really this problem is just testing your ability to read a graph and to know what the line of best fit means. Alright, our next problem is another graph that we have to interpret here. They're given a bunch of information. It says, as part of a recent wildlife conservation effort in Guatemala, park rangers in Tikal National Park have tracked a growing number of white-nosed coati living within a certain protection region over the periods from 1994 to 2004. So, according to the data above in this graph, if the population of coati in the protected regional region of Tikal National Park increased at the same rate from 2004 to 2006 as it did from 2000 to 2004, then what was the number of Cody in the park in 2006? So we need to look first at the rate of increase from 2000 to 2004. So here's 2000, here's 2004. So we've got to come all the way up here and then all the way here for 2000, and we do the same thing for 2004. All right, so the rate of increase is a slope. So this is going to be the equation of a line type concept. So if this problem is weird or challenging for you, this is the concept you're going to want to go back and review, how to find the equation of a line. In this case, we're looking for the slope of this line because it's a rate. A rate is a slope. So to find the slope, in general, it's the change in y over the change in x, or the change in your vertical over the change in your horizontal. So we need 2 points, an x1, y1, and an x2, y2. Well, our first point is going to be at the year 2000, and when it's at the year 2000, the number of Cody looks like it's at 140. So that's our y. And then our x2 is going to be at the year 2004. And the number of Cody at 2004, we drew a line to 180. Okay, so we have our x1, y1, our x2, y2. Now we just plug these values in to our slope equation. So if these are our y's and these are x's, our y2 we said was 180, minus y1 we said was 140, all over x2, which is 2004, minus x1, which is 2000. So this is the rate, again, or our slope. Now we just simplify. 180 minus 40 is 40. 2004 minus 2000 is 4. This reduces to 40 over 4 is just 10. So a slope of 10. So the units for this slope now, the units for our y is number of Cody. So this would be Cody, and our x units is going to be year. So 10 Cody per year. So on average from 2000 to 2004, the amount of Cody increased by 10 every year. So at this rate, from 2004 to 2006, the amount of Cody is going to increase by 10. So in 2004, there was 180 Cody. So 2004, there's 180, which means that in 2005, it's going to increase by 10, so there should be 190, which means that in 2006, it increases by 10 again, which would be 200. So in 2006, there should be 200 Cody, which is C. Alright, well, you've just solved several more problems from the SAT math test. We're going to keep chipping away at these problems, so be sure to watch the next video in this series and subscribe to the channel so you stay updated on all of our content. And again, if you're looking for more personal interaction, Gradegetter offers one-on-one private tutoring, so check out our website at gradegetter.com. Thanks for watching, and until next time, God bless.